Okay, so good morning, and as usual, we start with a summary of last week, week 9, where the topic was Monte Carlo simulations, which are the integral part to really study equilibrium statistical properties of any kind of system of choice. We looked first at the heat bath Monte Carlo method, where you thermalize the system looking at one spin at a time, which is really an example of how you can be super slow, motivating that we should do better. Next step was to look at random sampling, the state space, where we realized that we need really large numbers of states. This is especially true if we have states contributing particularly, observables being particularly peaked in their values, to make sure that we really sample this narrow region of states that contribute most nicely by random sampling is very hard. Observables. And so this laid then the foundation to motivate importance sampling. And the idea of importance sampling is that we calculate the average of an observable A by sampling n different configurations and measuring the property AI in these configurations. But now these AI states are not randomly sampled, but they're sampled according to a probability distribution, which allows us to particularly nicely sample our observables where they're peaked, so that we're really doing with a small number of states well in capturing the state space, and there's no other function that samples our state space better than the Boltzmann weight. So we here draw then states drawn from Boltzmann distribution, namely with a probability that's proportional to E minus beta, and the Hamiltonian describing the state. And so what we need to draw states now from this distribution is to have a biased random walk through state space, which we achieve via Markov chains. And so to really nicely now sample our state space, we had a small set of rules. First rule was that the process to hop from one state to the next has to be Markovian, which is a vocabulary to learn that tells you that the system doesn't have any memory. So what in the context of Monte Carlo sampling, it means that the next state will only be drawn by what's known about the current state and not any previous state. Then the concept of ergodicity, which says that I can reach all states in a finite number of moves between states. And this puts particular constraint on the choice of how I move in the state space, so to avoid circles and really allow us to reach those states. And and then the concept of detailed balance. Which says that the probability, the transition rate to go from a state S to a state S prime, given the probability to first of all be in the state S, should be symmetric, so that the probability to go from S prime to S, the transition rate W times the probability to be in this prime state first, these are equivalent. And this concept of detailed balance results from the use of the Chapman-Kolmogorov equation for Markov processes, which states that the probability to be in S2 at time, S3 at time T3, given that I was in S1 at T1, is given by summing over all intermediate states S1 and the probability to move from S2 to S3 and the probability to move from S1 to S2. And by using this Chapman-Kolmogorov equation, we derive the master equation, which states that there's a differential equation for the probability to be in a state S at time t, which is then given by the probability to be in a state S prime at time t, and the transition rate to go from S prime to S, which is the gain term, and minus the probability to already be in the state S time t, and the probability to leave the state, to go to, so this is the prime state, to go from S to S prime, which is the lost state term. And now you can see how this detailed balance condition results, because if we now look at the master equation, what we want to sample with our Monte Carlo simulation is the equilibrium distribution, hence the steady state of the system. And a steady state means that the system reaches a state where there's no explicit time dependence on the probability anymore. And I can achieve this by setting the inner part of this brackets to be equal 0, which is equivalent to the detailed balance condition. Stationary state, i.e. equilibrium. And so now to really, given that we know what we need to obey, there are different transition rates that we can assume for this W function. And so one prominent one is the metropolis importance sampling, where the probability to go from S to S prime is e to the minus beta e prime minus e for e prime bigger than 1, bigger than the current energy, and the probability to go there is 1 if the energy is less. So I go down in the energy. Alternative was the Glauber dynamics, where this is half minus beta E prime minus E1 plus. And you can lump these expressions into this condition of detailed balance to see that this is satisfied. And then last thing we did was we looked into the ingredients. For Monte Carlo simulations. And touched the issue of boundary conditions, where we have to be aware of the potential to have finite size effects. We looked into the concept of the initial condition, how this impacts our result, and found the need to equilibrate, and notably discussed the concept of independent samples, where we calculated the average error in our observation of an entity A, observable A, which if the initial states are not fully independent, then apart from the statistical error, I get another error which scales, which with a factor of 1 plus 2 TA over dt, with TA being the correlation time and defined by A at 0, A of t minus A squared over A normalized that way, which is the same as integrating an exponentially decaying correlation where TA is the correlation time. So what this means is that if I draw my sample, so what I can vary in my simulation is the time delta t at which I draw my samples. And so if I draw my samples at longer and longer intervals, then if this is big, this drawing of the interval is bigger than the correlation time, then you see that this factor goes to 0, and I'm just left with my normal statistical error. If I draw them closer to each other, then I have to pay attention of this additional statistical error. So time steps at which samples are drawn. Okay, so that was last week, and today we're going to start into the randomization group. Where we're going to first talk about the idea and then look at RG for the 1D Ising model, which is to explain the concepts in, again, the simplest case there may be. So let's get started. The randomization group. And here I'm following Newman's chapter 8 and chapter 9. So the randomization group is now the really most potent method that we have in identifying the dynamics at criticality, because so far we cannot explain a number of observations. First of all, that continuous phase transitions fall into universality classes, so that different systems obey the same critical exponent, is we can't explain. It's characterized of critical exponents. So there's some underlying connection that we're missing so far. Another aim is also for a given universality class to explain that there is an upper critical dimension above which exponents follow the mean field results. And then we had, in the very early part of the class, we derived dependencies, interdependencies, inequality conditions for critical exponents, but they are not actually inequality, but equality conditions. And how they follow is also not clear yet. So relations between critical follow from thermodynamics as inequalities that hold as equalities. And another observation is that these critical exponents are the same if I approach from above or below, reducing or increasing the temperature, which is also an observation so far that we cannot explain. This is approached from above or below. And last, we observed that the 2D critical exponents so far often appear to be fractional, rational fractions. And so what we realize here, what we're missing is that we have these series expansions which allow us to go from low and high temperature using dualities, learn a little bit about the behavior as we approach the critical behavior. We have our field theories with the saddle point approximation that's equivalent to the mean field approximation, where we can look at what is the role of fluctuations as we approach the criticality, but we're really missing what's really happening at this critical point. So we need a theory for what is happening at the critical point. And that needs to be based on the physics at the critical point. And so what do we know about the critical point? Well, we know that the correlation length diverges, and we have this self-similar behavior, that the system at criticality looks the same if I look at it on a scale of a millimeter or a centimeter or 10 centimeters. It's the same structure And this is really a property that's unique to the critical point. And so maybe looking at, picking out this unique property that characterizes the critical point, we can generate a framework that tells us really about what's happening at the critical point. And this goes back historically to 1971 and Wilson, who then published the first paper describing the renormalization group. And it quickly became accepted as a very powerful and novel method that won him a Nobel Prize just a decade later, which I suspect is fast for Nobel Prizes. Okay, so what is the idea? The idea is that within the renormalization group, we change the length scale of a system by removing degrees of freedom, and only if we really add criticality, will the properties of the system remain unaltered by taking away these degrees of freedom, hence the reduced equations that we find then really describe the dynamics at criticality, where we have these long-range correlations, and we can use the self-similarity by changing the length scales. And we know that if we coarse-grain out the different degrees of freedom by making use of this change of length scales, that only at criticality the behavior should stay the same. And so those that persist then describe our dynamics at criticality. So renormalization group changes the length scale of a system by removing degrees freedom, and only at criticality the properties of the system remain unaltered by the change in scale, and hence, the critical behavior described by the fixed points of these changes in length scales of the renormalization group. Transformation. Let me illustrate this idea graphically by the so-called Kadanoff blocking developed then by Leo Kadanoff. Version. Who I feel related to. So Kadanoff was the PhD advisor of my postdoc mentor, Mike Brenner. And I remember him actually, he passed away now, but when I was still a postdoc, he came to visit at Harvard, and he really gave a very deep talk about the whole concepts of statistical physics as a very inspiring character, despite this obvious scientific contributions. So the idea was of this Kadanoff plot blocking is that I repeatedly coarse grain, say my spin lattice, and thereby generate a new system, but and thereby because it's a shorter, like the distances are larger, I reduce the correlation length and therefore move it away from criticality. But I learn about how the system would approach like the dynamics to reach criticality, and thereby I can identify these fixed points of the system. So I generate the dynamics of the system by changing this length scales, and then can identify, because I have access to the dynamics all of a sudden of how the system behaves as I move away. I can also then see how it would move toward and identify these fixed points, and then at the fixed points of the system really just have the equations that describe the behavior at criticality. So I transform the problem into a similar one, which is further away from criticality. So what does it mean? So let's take a symmetric spin lattice, and what I do is I coarse grain by, say, introducing this light blue lattice, which is coarse graining over the spins, these 4 spins at the lattice side, and I make this a super spin such that my new system is then has a different length scale. Like it's in this case, it would be the distances are twice as large. And then here I define new spins, and then each spin comprises the info of the previous lattice. And principal can keep going with this method on and on. So I keep coarse graining. So what we see here is that the new lattice with sides I has now twice the lattice spacing. Old one. And I define the new spin spin block. That's why it's called Kadanoff blocking. Sorry, let me just correct that. Spin block. I by Si is then the sum over all spins that are contributing to the spin block I, in this case 4, together. And if I now use this definition of how I define spins in my transformed lattice, I can also write obviously the energy of the underlying model, let's consider the Ising model, in terms of this new spin. So then I can write the, say, Ising model in terms of the new spin Si. And I obviously get similar interactions between these block spins. But the difference is that it's in terms of block spins. Now in terms of block spin Si. But with new interaction strings. K prime, which is some kind of function of the previous interaction strings. But since the lattice spacing became twice as large, this reduces the correlation length, right? But the new system has a reduced correlation lengths. And therefore, what we do if we, imagine that we keep blocking and blocking, like putting more and more spins together, we keep on moving further away from criticality. And then from the dynamics, I can determine the fixed point, and I know about the fixed point similar to our results for the series expansion of going from low and high temperature, that the fixed point has to map on itself. So the fixed point is independent of the way of how I do the mapping. At it to be determined fixed point, the correlation length must map onto itself, and that's obviously only possible if the correlation length diverges, which is at criticality. So thereby we really identify criticality, and with this method we really also, as you will see, get at the critical components, exponents of the dynamics at criticality. Okay, so that's the recipe and the idea. And now let's try to apply it in a specific context. By taking as an example the renormalization group for the 1D Ising model. Okay, so the 1D Ising model means, okay, it's 1D, and we have lattice sites. These are my dots here. And what we want to do now is we want to do these block spins, which on the 2D would mean that I go in and I lump spins into pairs of 2 neighboring spins. So we want to describe the n-spin chain in terms of two spin blocks. So really doing this Kadanoff blocking here. Two spin blocks. And this process of coarse graining is sometimes referred as coarse graining and sometimes as decimation, because you reduce the number of spin sites. So let me just add, so this is the original spin. That's the, oops, how did I go to gray? Interesting. Original spin. This is the spin block. And what happens to the lattice side is now that if the original lattice spacing is A, then the ones of the spin blocks, okay, is then 2A. And now our task is to see how does it affect our Hamiltonian, our partition function. So we first look at the Ising model with a zero applied field, which is always easier. Then our partition function reads summing over all individual spins, states, plus minus 1. And then we have here a exponent k s1, s2, k s2, s3. And so until e to the k sn minus 1 sn. And we can use as before that we can write the exponent si plus 1 as cosine, hyperbolic cosine of k1 plus, oh, sorry. Times 1 plus si plus 1 times hyperbolicus. Okay. And so since all these exponents are product of each other, this moves out and I'm left with so then the sum, if I sum over si plus 1, si plus 1 pops up twice in two terms. Those two, and these then become cos h square, and here summing over si plus 1 equal 1. And now taking the product of the two of those terms, 1 times 1 becomes 1 plus 1 times si plus 1 times k plus si plus 1 si plus 2 times k, and then the square term, which is si plus 1 squared, si plus 2 times k squared. And now summing over the having si plus 1 plus and minus 1, obviously these terms that are linear in si plus 1, they come up twice with a plus and a minus, and therefore cancel out each other, and only these two terms prevail with the same contribution. So we get a factor of 2 out, 2 cos hk squared, and then 1 plus si plus 2 times k, which we can reformulate as this actually being a constant times actually summing over of a chi prime si plus 2, looking back at this formula again, right? So what we did up here is that we used like the trigonometric identities to write the exponent of k si plus 1 as a constant times 1 plus si plus 1's and a factor here that's related to this k. And now we're just doing this reverse, right? So we ignore these constants, or we just write this as a constant, but we also find this functional term here. And we identify that here we have now si plus 1, but instead of a tanh k, we have a tanh k squared. So that's why if we rewrite it in terms of this exponent, I have a k prime here. But now, so where k prime is such that tanh k prime is tanh squared k. But this was actually the key step of like introducing the block spins already, right? Just summing over two successive spins and rewriting the Hamiltonian to have the same functional forms, but now with a different interaction strings. So this gives an Ising model with now just n over 2 spins on a lattice. So I go from I to I plus 2, so with a spacing of 2a and a coupling k prime, where, okay, it's just repeating, tanh k prime is tanh square k. But now you can see that, well, you know, okay, so I can introduce the block spins once, but I could actually, you know, keep on blocking, right? I mean, I could now block those block spins even one iteration further, and now introduce these even larger block spins. And what would happen is we would play exactly the same spiel here to then arrive at an si plus 4. So again, doubling the spacing and recursively changing the interaction strengths. So what we find here is, oops, this is a renormalization recursive relation, which can be iterated an arbitrary number of times. And what I would find is that of the nth iteration, the k of this of the n plus 1's iteration, it should just be the interaction strengths of the nth iteration to the power of 2, with k0 equal pi. So we found now a recursive relation for what happens to the interaction strength. What we're interested in now, so we have these, we find the dynamics in as we go away from criticality, and now we say, okay, so what are actually the fixed points of this of these dynamics, because these fixed points will tell us at about the dynamics at criticality. So we look for the fixed points. And we know that at the fixed points, I need to have tanh k star is equal tanh k star square. There's a fixed point. And that's for this we have two solutions. One is that tanh k star is equal to 0, which is equivalent to k being 0, and we have 0 is equal 0 on both sides. Or we have tanh k star equal to 1, because then we have 1 and 1 squared equal 1 on both sides, and that corresponds to k being at infinity. Okay, so now we have the fixed points, and we have two. We only expect one critical point, right? So what's the so we need to learn about the quality of these fixed points, and the way you determine quality of a fixed point is to look at its stability. And the idea is if you have multiple fixed points in a system, then you have fixed points that are stable, where the system will eventually end up in, or unstable fixed points that the system will always leave. So we need to study stability by looking at the KNs. And sorry, this is meant to be a small, let me make it a visible kappa. Okay, kappa. And then the recursive relation with this kappa definition becomes that k n plus 1 is kappa n squared. And now we know that this kappa n, given that how it's defined, that tanh can for positive interaction only be between 1 and 0, right? That's the values that this can take, so that defines this kappa. And that's just to make these maps easily linear, because now what this means graphically is that we have here the k space, and it goes between 0 and 1. And another 0 and 1. Okay. So this is then kn, and looking at the successive kn plus 1s. Sorry. Oh, it's not to the power of n, I'm sorry. K kappa n plus 1. So we know that they are related by the square. So it's this function dependence. So what it means is if I start off with a specific kappa, say here, a kappa 0, then the kappa 1 will be that value. And if I map this back down here, this is then a kappa 1, this is kappa 2, and so on. So you can see that graphically what's happening is in this so-called cobweb diagram, the system will flow away from the fixed point at 1 to the fixed point at 0. So kappa equals 0 is the stable fixed point, and this kappa equal 1 is an unstable fixed point. So that was the quick graphical solution of, what is the dynamics in between these two stable fixed points. Mathematically, if you're in higher dimensional space, that might not be so easy. So mathematically, what you do is to arrive at this is you make an ansatz of xn being 1 plus x n hat, so small deviation, and then you start iterating and solving for xn plus 1, which is 1 plus oh, sorry, 1 minus, I'm sorry. I don't want to go above 1. I need to stay below 1, sorry. And I can do the same to define my xn plus 1 as 1 minus x n minus 1 hat, xn plus 1 hat. And then because of this quadratic relationship, we know that this is 1 minus xn hat squared. And so if we solve this equation, taking into account that these deviations from 1 are small, we find that this is 1 minus 2 xn hat plus xn hat squared. This is higher order. And so from this, we can read off that xn plus 2 is 2xn. And so we see that this is like an expansion about the fixed point at 1, and we are driven away from the fixed point because the distance I am from the fixed point, this xn hat, is getting bigger and bigger over time. Sorry, it's a hat missing. So this would also mathematically allow us to draw the conclusion that the fixed point at x equal 1 is unstable. So we can also think about this following terms. So it's custom to denote stable fixed points with a filled dot and unstable fixed points with an unfilled dot. So this is the one at 0 and at 1. This is tanh k equals 0. This is tanh k equal 1, and I'm floating this way. Taking into account how k is defined in terms of the temperature, so with k j over k dt, this means that I'm flowing, it's the unstable, stable, from T equals 0 to T to high temperature. This is the unstable. And this is the stable. Yeah.
Question. So you said that when we course grain with each iteration, we go away from the critical point.
Mm-hmm.
So this means that the direction of the flow points away from the critical point, right? Because when we go with the flow, we increase n, so we increase in the interaction. So wouldn't you expect that the unstable fixed point is the one that describes criticality and not the one that is stable?
Yeah. We're going to seek the unstable. So the unstable critical. So far, I said that we care about the critical points, right?
Yeah.
Because the critical points tell us where the system is independent of the scale invariant, because we change the scale of the system by doing this blocking, and it's only possible to have. But obviously, I can find more potential critical points. And now the question was which one is what's the dynamics of these systems, and what we see here is that we'll eventually will classify the behavior criticality at the fixed points that are unstable, and we'll denominate the behavior around I mean, the 1D Ising model has its flaw because there's no phase transition, right? But but it's still like the one where you can nicely introduce the concept, and everything is here already, right? So we do the blocking, we find a relation for the interaction strength, we look at the renormalization flow. This is in a very simple setting. Here we're looking at the renormalization flow, this is going to be, you're going to see the event next year, that you can embed these renormalization flows in principle in a d-dimensional, like in a high-dimensional space. But it turns out that there's a manifold where you have the unstable, a manifold that lines out the unstable directions of the fixed points, and this manifold is really the critical manifold in this higher dimensional space in general for any system, and this manifold then determines the behavior at criticality. And the cool thing is we find not only the fixed point, which we also did with the series expansions, right, and duality, but we also find this manifold, and so we can determine the behavior within this manifold at criticality. That's the cool thing. So what? Okay, so this is the in a nutshell the concept of Kadanoff blockings for the 1D Ising model, but this obviously can be generalized. We would be interested in a generalization. That we don't necessarily need to decimate or coarse grain over 2 spins, but this could be B spins in general. So we have then every B side a block. Also trace over decimate coarse grain. Blocks of B spins, leaving a spin every B's side. So that would be the first generalization, with the idea that if I go back to my 1D, and these are my original spins again. Original spin. And then I can also now sort of coarse grain in a fashion that I then have this being B times A. And within this generalization, just to exemplify it again on the Ising model, we can use that what we're doing here is then summing from SI plus 1 plus minus 1 to all S to SI plus B minus 1 and in general SI plus 1 K SI plus B minus 1 SI plus B, and doing the similar summing over summing out all the spins in between, so that I'm only at the end left with the SI and the SI plus B spin. I similarly arrive at then 2 to the power of B minus 1. For each sum I get a cos HK to the power of B, and I'm left with 1 plus SI plus B tanh K to the power of B, which is then equivalent to having a constant times now e to the K prime SI plus B, where tanh k prime is tanh k to the power of b. And what you hopefully, like this would be like just a generalization of how you can perform the blocking. But just looking at the relationship that I get, obviously this will, how the interaction strings transforms, obviously the fixed points are unaffected by how I do the blocking. And also the stability of these, of the fixed point is unaffected. Showing, which is important to note. Okay, so for now, we restricted ourselves to the case of zero applied field. Let's make it a little more exciting by now. Suppose we have an applied field and we go for b equal 2. So we do the 2-spin blocking. Remember, for the applied field, when solving the one-dimensional Ising model, we had introduced the transfer matrix approach. So we wrote the partition sum as the trace of the transfer matrix to the power of n, with the transfer matrix being defined as I to the k plus h, small h being big H defined times beta, I minus k so recall that k was beta j and small h is now beta capital H. And so if we go back and split up now this trace of the transfer matrix, what it actually meant was, because we want to do this spin blocking again, right, was the sum over all states of the spins. And this was actually looking at the transfer matrix from 1 to 2, from 2 to 3, and so on until t n minus 1. And then I had n of those, and they were identical, and that's why. And the summation resulted in a trace. That's how we resulted here. But now, as we want to do spin blocking, right? So we want to only sum out, say, spin 2. What this actually means is that we can write this. May rewrite now as only summing over, so only summing over the odd spins, because I summed out the even ones, which then says that I have the transfer matrix going from 1 to 3, and that's the square. And then square 3, 5, and so on. To really solve these transfer matrix, we have to specify a boundary condition. So consider a closed chain, i.e. periodic boundary conditions. Where Sn plus 1 is back to being S1. Which would be like, oops, not so good. Oh, Sn plus 1 is S1 S2. Okay, so with this in mind, so what we then, if we now compare this definition of the partition function, what we see is that what we're doing is actually taking here the trace of t square to the power now of half the states, because we're only summing over the odd ones, over n half. And now I can just define this now as taking the trace of a t prime to the power of n half, where t prime is t squared. So what is now, the dynamics of this renormalization? And to study this, let me introduce u as shorthand for e to the power of minus k, which you see popping up here, and similarly v for e to the minus small h. Here, remember, h and k are both bigger than 1, positive values. So we know that then u and v are between 1 and 0, 1 and 0, yeah. Then we can write the transfer matrix in a closed form as this being, so we define it with a minus k, so this is 1 over u times 1 over v. Here we have a u popping up, another u there, and here we have v over u. And since we then have the transfer, then we can define what's actually the t prime. So the t prime is then obviously the product of two of those. And so that's then 1 over u squared v squared minus u squared, plus u squared, sorry. And that's 1 over v plus, here the u's cancel then out, plus v. And same down here. And here we get this times this, so we get a u squared plus v squared over u squared. And that's then, so that was t squared. Now I want to write this transfer matrix as some kind of constant I don't care about, but of the same structure, right? I want to have a u prime, v prime, u prime, u prime, v prime over u prime. Whoops. Kind of structure. And so that gives me, if I put this equal to that, that gives me 3 equations of how to determine my u prime and my v prime. So we now solve for u prime and v prime. This constant I call c. And so note, so there are 3 independent equations, right? Because it's a symmetric matrix. And we also have 3 unknowns, right? We have u prime, v prime, and the c. So 3 equations, 3 unknowns. This should be a happy ending. And so we have c times u prime is 1 over v plus v. We have c over u prime v prime is 1 over v squared plus u squared. And we have c v prime over u prime is u squared plus v squared over u squared. And without going into the math, let me show you the result, which is v plus 1 over v. And that's why you now appreciate why we started with the simplest model first place, because obviously these get tricky, these get evolved algebraically quite quickly. So, and then C is U plus. So what we can, if you, just to ingrain this, so if you realize that your results are that evolved, it's very likely that you did a mistake. So it's good to check by setting h equals 0, which is small h equals 0, which is equivalent to sending v to 1. And if we do this, we find that u prime is 1 plus 1 square root of 2 u to the 4 plus 1 over u to the 4 plus 2. And v prime is sorry, I'm just reorganizing terms. And so now what we actually have here, we can expand this as, sorry, with this, aha, talk to me, yeah, is, okay. Sorry. So so what we can see is that we can expand the denominator. This is a quadratic function of u squared plus 1 over u squared to the square. So we can take out the root and then remind ourselves that this u prime is actually, where did we define u prime? Okay, so we defined u. So from the u prime, we get e to the minus k prime. So we go back and getting a relation for the k prime. And just to be adventurous, try. So this is square root of 2 over set u squared plus 1 over u squared square root. So that's e to the k prime is equal to u squared minus plus u minus 2, which we can move, take the square on both sides to find u squared plus u minus 2 over 2. But then we have that tanh h k prime is actually defined as e k prime minus e sinus hyperbolicus divided by cosinus cos plus k prime, which is nothing else but e to the 2k prime minus 1 over e 2k prime plus 1, which we rewrite then as u squared minus 2. If we just put in these results here, right? And multiply with the 2. And here we have u squared plus u minus square plus 2. This is again a quadratic function, so I can write this as u minus 1 square u plus u minus 1 square. Let me expand this again and adding a 2 here, because then it becomes obvious what we have here. It's above, it's a we can write this again as a sinus hyperbolic cos squared of k divided by cosine squared of scale, and it's just tangent k square. So that's exactly the relation that we had for the Ising model without an applied field. Okay, well done. So, but apart from the check, so these equations for u prime and v prime and c, they now determine our renormalization group dynamics, and so we can now again do the spiel of looking into what are the fixed points and what are the dynamics in the quality of these fixed points. And so the fixed points are first of all the 0, which is 0 interaction or infinite temperature, where v prime is arbitrary, so for any field, or I can have v to be equal to 1. That's, remember, it's e to the minus h, so that's actually the 0 field, where that's why we did the exercise before. We recover the dynamics that we've known before with tang k is equal tang k prime squared as before. Let me draw this down here. So now mapping out the dynamics as in a space of V, which is minus h kbt versus U is minus h k, oh sorry, j over kbt. So remember, U and V both go between 0 and 1. And now I have a fixed point at 0 field, V equal 1, where this is determining the dynamics of my flow. So, and then I have another fixed point, which is at k equals 0. So that's actually this entire line here. So maybe let me switch to a different color. So and to just complete this drawing before we have all the results already. So these are the stable fixed points, and this is the unstable one. So this is a whole line of stable fixed points. And now the dynamics as show me that in this space, I would flow that way to I would flow from the unstable to this whole line of stable fixed points. And so now, since we have a system where we actually have at least a singular point where we have a phase transition, we are successfully able to identify, as we discussed just before already, but here's illustrated now, This is the critical point where we have long-ranged correlations. And as advertised before, this is the one that marks the critical behavior, the unstable fixed point. And this line of stable fixed points, this is the paramagnetic state where which is disordered. So what I hid from you is how to identify that these what the quality of these fixed points are. And this is resulting from linearizing so the stability results from linearizing around let's say in this case the unstable fixed point, which is v equal 1 and u equal 0. Then we not going too much into details because these are lengthy expressions, but basically what we do is now so you find the fixed points by setting u prime equal like u star equal v star u star. So this is the recipe that finds the fixed points, and now to do the recipe to identify the stability of the fixed points is to linearize this expression around the individual stable fixed points. So in this case around v equal 1 and u equal 1. And so if you do this, you find u prime is x equal to 4u plus higher order terms v prime minus 1 is equal to v prime minus v star is 2v minus v star, depending on, and so we can write this as then u prime, v prime is 4, 0, 0, 2. These are the linearized dynamics in the space, and the eigenvalues of these linearized dynamics in the phase space of this transformation then give us that we here have one eigenvalue 4, which happens to be b squared, and another eigenvalue that is 2, that is b. The important message to take away is by linearizing the system around our fixed points and identifying the eigenvalues, we find if the dynamics are stable or unstable. So for positive eigenvalues, we have positive eigenvalues. Unstable direction and negative eigenvalues point to that's a stable direction. So along the negative eigenvalues, I'm flowing towards the fixed points, and along positive eigenvalues I'm flowing away. And so now if both eigenvalues are positive, I only have inflow, I only have outflow, I have an unstable fixed point. If I have both, I could have a saddle point. For both eigenvalues to be negative, I would have a stable fixed point. So this is how I define the quality of the fixed points. And as we'll discuss then next lecture next week, which means next year, there's actually a meaning in these eigenvalues being related to how we performed the decimation. So these are two examples to illustrate you the idea of the renormalization group. And so what we do is, due to this consecutive coarse graining, which drives us away from criticality, we are able to determine these dynamics in the space of behavior. And this allows us to determine the fixed points, to determine the quality of the fixed points, and the dynamics in this phase space, which then allows us to also make statements, as will follow, about the behavior at these critical at criticality. But that's the gist of today. And with that, I would love to thank you for your attention and stop the recording. See you next year.